Good afternoon, everyone. Welcome you all in the hands-on session for this FSS FBP, and today is day 7. So in all the previous FDP sessions, hands-on sessions, we have covered all type of absorbers, base structure, and the metamaterial structure. Along with that, we have also covered the array base structure, how we can simulate this array structure by using the waveguide port. And till now, if you have any query regarding all these topics, then you can write down in the chat box. And today I'm starting our session by using with the help of some basic concept of the PCR, because the absorbers we have already covered. So today I'm starting with the polarization converters, which is the another application of this frequency selective surface. We already know uh, with the help of the unit cell metamaterial, we can create a meta surface, and we will call this as a frequency selective surface. And the major application of this frequency selective surfaces are absorbers, polarization converters, filters, and many more. So let's start our session with the PCR. Before starting this session, I will tell you the all the topics which I am covering in this session, in today's session. So my first topic is basic concept behind PCR. Second, type of PCR designing with the help of some papers. Then design of a reflective type PCR, because when we are talking about the type of PCR, means type of polarization converter, then mainly we can call that is as two type of PCR is there. One is reflective type PCR, and the second one is transmittive type PCR. In reflective type PCR, there is a complete ground plane at the back of the structure, and in the transmitting type PCR, the ground plane is not there. Complete ground plane is not there. Some structure should be there so that we achieve some transmission coefficients, and with the help of these transmission coefficient, we can calculate our polarization conversion ratio, which is the essential parameters for this polarization converter. Then we can also we have to see in the reflective type PCR, its boundary conditions, its formula, how we can calculate this polarization conversion ratio. Then we will also see the incident angle stability, and the difference between this absorber and PCR is, in case of absorber, we can, in the angular stability analysis, we can calculate the polarization angle stability. But in case of this polarization converter, we cannot calculate its polarization angle stability. Okay. Now, after completing this PCR term, after completing this polarization converter, for the designing purpose, I am only taking the reflective type PCR. But you can also, with the help of these reflecting type PCR, you can also make a transmittive type PCR also, and you can analyze it by its own. And then along with this PCR term, I am also covering the unit cell bending. Means in the concept of this bending and conformal, there are two terms which we have to analyze. One is bending for only single unit cell, and the another thing is bending for the complete array structure. Means we have the unit cell, and we have to create a array of this unit cell. And array is any type of, whether it is 1x1, or whether it is 1x3, 1x5, or 2x2, 3x3, 5x5. Any type of array we can make with the help of single unit cell, and we can also analyze how we can create a bending. Okay, so we can easily observe the conformal analysis, means how much bending this any structure will have. Okay, along with this bending terminology, we have in this session we can also see the basics of HFSS. Okay, because all the CST part we have covered for this in the end of this session, and we will also see the basics of HFS, and then we will also see how we can transpose, how we can transfer the CST design into HFSS, because in CST and HFSS we can separately design the structure and we can simulate, but there is a facility we can also import and export the CST or HFSS file to the another software. Means we can import the CST design and we can export it. We can export the CST design and we can import it in HFSS also. And in HFSS, we can simulate that design, and vice versa will also possible. We can export the HFSS design file and we can import it in CST. We can import it in CST and we will see its simulation technique. Okay, so all these topics we have to cover in this session only. So I can start my session with the basic concept behind this polarization converter. Okay, I am sharing my screen. Just a minute. This is one of my paper based on this dual band terahertz reflective linear cross polarization converter based biosensor. Okay, because this is a type of multi-band PCR. So here dual band PCR is there, and I'm using it in a terahertz operating range, and this PCR is working as a reflective type linear cross polarization converter. This reflective means see this graphical view. See this graphical view. Forget about this structure, this first one, because it's a container and all right. I'm not covering this area because this is a part of sensing. I'm just covering this 3-layer structure, which is the bottom layer is this ground plane. This is a complete ground. Because of this ground plane, I'm calling it about this reflective. Okay, and this is the substrate part, and the top of this substrate I am designing one structure which is responsible for the cross polarization converter. Why I'm calling it as a cross polarization converter? Because it is converting the co-polarized incident wave into the cross polarized reflective signal. This is the I just zoom this structure. This is the direction of the incident signal, in which this black line, this black arrow is the KZ direction, which is the direction of incident angle. The incident signal is directly come to the top surface of this polarization converter. This is the electric field direction, and this is the magnetic field direction. Okay. And when the signal is transmitting, when the signal is incidenting on this top surface of this PCR polarization converter, then inside this substrate and after reflecting back using this ground plane, it is the reflected signal is like this. In the incident signal, the vertical axis is showing the magnetic field direction. Okay, but after this reflection in the vertical direction, there is a electric field component, and here in the horizontal axis, there is a electric field component in the incident signal, but after reflection in the horizontal side, there is a magnetic field component, and that's why it is called as a cross polarization converter. Okay, this is the basic concept behind this PCR. This is the step-by-step. This is the step-by-step designing process of this PCR. First, I am designing this hexagon patch, the complete patch. Then, with the help of another hexagon patch, and if we edged out the inner part of this hexagon patch, then it will designed as a hexagonal ring. And after that, there is a slot cut in this direction, in the diagonal direction, and that diagonal cut will be responsible for making this structure as a polarization converter rather than a absorber. Okay, so now we will directly go to the CST and we will design this structure, and we will see how its S parameter will behave and what the its PCR value, polarization conversion ratio. Okay, this is the formula for this PCR. See this equation 1 and the equation 2 is the formula for PCR. In CST, where we have putting our absorption equation in the same area, I have to write it like this. This is the formula for the polarization converter. Okay, this all the terms are mentioned here. What's the significant, what it is showing, what is the value for this RXY, what RXY is showing, what RYY showing, all are mentioned in this paper as well. And after and in CST, we will see what's all these components. Okay, what the nomenclature we have used for this PCR terms. Here this PCRY means our incident signal is the Y polarized. Okay, and this PCRX means our incident signal we will take care of about the X axis. And if my incident signal is X, then how much signal is converted into the X component, means from Y polarized to X polarized, that we will see using this formula. Okay, now these are some results. This first result is co and cross component of reflection from design steps. Step by step, the reflection parameters and co and cross component, we have to take care of these both terms. Okay, and step by step, this is the reflection coefficient, this is, and then in the final step, this is the reflection coefficient. And we will also see what's its final PCR results is showing. Okay, it should be near about 90 or more than 90, which is preferred. These are some results of its sub-elements, means in figure 3, Y2X polarization converter, how we will see structure is, if my structure is bipolarized, means this is the y-axis, this is the x-axis, and my incident signal is along the x-axis. That's why I'm taking it as a EI. I means the incident term. And after this polarization, with the help of this polarization converter, our y-polarized incident signal will transfer into this x-polarized. That's why we will call this as the cross polarization converter, and in between these two axes there is a U and V axis where our term will this is the sub component of EIU and ERU term. This is my ER, this is the U axis, so ERU is here, ERV is here, and likewise this is my EI term, so this EIU is here and EIV is here. So we will also see along this U and V axis how my reflection and transmission will take place. The co and cross polarized reflection coefficient for U and V polarization. Okay. In between this U and V or X and Y, there is a 90-degree of phase shift will take place, because here this is V, this is U, and in between these U and V, the angle which is created here are 90-degree. And similarly, this Y and X, the angle is 90-degree. Okay. So we will design this structure in CST, and then we will see how we can put this formula for achieving this type of PCR result. This is the PCR result. Okay. So go to this step-by-step structure and see all these terms. First, we will look what is the thickness of our substrate and what is the thickness of our ground plane. Then only we can make this. So we have to see this also. For that, go to this design and analysis part. A cross TS is the unit cell dimension for this structure, where TS is 4 micrometer. Our substrate thickness is 4 micrometer. Okay. And what is the thickness of completely gold plated? The thickness of metal TM is 0.1 micrometer. Okay. And the resonating structure thickness is also 0.1 micrometer. So the complete thickness of this PCA polarization converter is 4.2 micrometer. Okay. And the unit cell value A is 20. This is 20. Okay. Yeah. For this work, this unit cell dimension in micrometer cube is 20 cross 20 cross 4.2. Okay. Just directly go to the CST. Just open the new CST file. Okay, this is the main screen. First, choose the template. If you save your template, then you can directly choose from here also, where all the settings have already been done. So, okay, just unit cell. This is the phase instruction diagram. The template is similar. Okay, there is no difference between these absorber and PCR template. So, what's the frequency? What is the operating? If you will change the operating range of this simulation, then there may be some change in your result, because based on this operating range, based on this minimum and maximum frequency and the step size of all the simulation type, this will simulate. So if you change the simulation frequency, then your result may slight there may be some change in your result. Okay, so this what's the frequency? 228. So the minimum frequency should be 228. No need to. Okay, Finish. Okay. All these things are common, so I will directly make the ground and substrate part because there is no difference in terms of absorber and PCR. Okay, so just take this X min and X max A by 2, Z min 0 to Tg, the metal is gold here, gold. A value is 20 and the Tg is 0.1. This is my ground part. In the view, I'm removing this boundary box. Okay. Again, go to the simulation. Make substrate. Minus A by 2 to A by 2. Minus A by 2 to A by 2. Now it is starting from Tg and it is Ts. Tg plus Ts. This is the thickness for the ground plane and this Ts is the thickness for the substrate. And the substrate material is polyamide here. This polyamide, glossy polyamide. This TH is 4. We just save this structure. So today is day 7. Well band PCR. I just save my CSV file. Now I have to make a hexagonal patch with this direction. So first we will see how we can create it. Let's go to the, you can make this structure also by using the upper and by using this outer radius and inner radius, you can directly make this ring. But go with step by step. So the outer radius is R1. Okay. Just go to this cylindrical shape, this cylinder. This outer radius is R1, radius is 0 because I have to make patch here. Not if you want to ring here directly, then directly put R1 and R2. Tg plus Ts and the Tg plus Ts plus Tg. Segment is segment is here because hexagon structure we have to make, and the material is gold only. The value of this R1 is 10, R2 is 9. Okay, that means the this ring is 1 micrometer. 10. Okay. Now see, this is the structure which is creating on the top of the absorber surface, but we have to rotate structure for this step 1. So how much rotation is required? If we make a 90-degree of rotation, then this edge is aligned with here. And if you want to make this edge with this square corner of this substrate, then make a 45-degree of rotation. So for the rotation, what we have to do, just go to this navigation tree. In the component 1, we have to choose this patch and then go to this transform, rotate. No, I don't want to make a copy here, so don't take this copy. Okay, only rotating in the Z axis and 45. Just preview. Yeah, this is the same orientation which we want. So, okay, this is the step 1. See, now just make a second patch. Here the outer radius is R2, inner radius is 0 because of the patch. Next, from TG to TS, TG plus TS. Okay, segment is 6, material gold, component 1. Just okay, R2 is 9. This R2 value, R2 should be 9 micrometer. Okay, and then the final, the gap between these two rings is W, which is 2 micrometer. First we will make the ring, so press OK. Okay, you have to rotate it within 45-degree, so rotate, don't take here, directly in the Z axis. You make a 45-degree of rotation, then preview and OK. This is the 2 hexagonal patch. So I have to remove this solid 2 from this solid 1. So first choose this solid 1, then go to the boolean, subtract and choose this solid 2 and click OK. Okay. Now this step 2 is also completed. Now we have to make a cut in these two. So there are two options. You can make a brick of length and width, whatever is required. You can make a brick here and you can remove this brick from this hexagonal ring. Okay, and make a mirror image of this brick to the another side. If you mirror along the x-axis, because this is your x-axis and this will be your y-axis. Okay. If you make a rectangular box here, and if you make a mirror of its this rectangular box along the x-axis, then this rectangular box will appear here, this side. Right now it is in the right hand direction, then it will come to as this right side. Right now it is in left side. And if you again make a mirror for this structure, then in the y-axis it will came here. Directly you can't make mirror copy in the diagonal direction. Okay, first you have to choose the mirror along x, then you have to choose mirror along y, then you have to paste it here. And another way is directly make a, because in between there is no geometry. In between there is no geometry, that's why you can make a complete length of a rectangular patch here, which will cover both the sides of this hexagon, and you can subtract with the hexagonal ring. So both the cuts will simultaneously appear in step 3. I'm using this step only, this third one step. Okay, so length, you can choose any length, but the length should be covered both these models, both these edges. Okay, so you can choose any length. The width should be 2 micrometer. So go to the simulation, choose the brick option, rectangular cut. In the x-axis, what I have to choose in the x, because I am placing my square rectangular patch here in the y-axis. So the in the x-axis, this is the thickness of our patch. So x min is minus w by 2. In the minus side, there is minus w by 2. In the positive side, this is w by 2. Y min, you can use the complete unit cell structure. So minus a by 2 to a by 2. Now this term is Tg plus Ts. Here it is Tg plus Ts plus Tg. Okay. And this is component 1 and the material is gold. Review. The width of this rectangular patch is 2. This one. Okay. First we will create a vertical rectangular patch. Just press OK key. First we have to align this rectangular patch along this U or V axis here, or we can put it here also. But first we should be place this rectangular patch in this direction, in this. So go to the rectangular cut, transform, here we have to choose again this rotate. Okay, and we don't want a copy here, so don't take this copy. We can directly rotate it along in the z axis with the angle of 45 degree. Okay, just preview this. See the orange line, which is the outer line of my rectangular patch, which is covering the complete hexagonal ring. if I cut this rectangular patch with this ring, then it will covering both the edges. Okay, click the OK button here. Now this one. Just click this rectangular cut. Sorry, this solid one. Go to this boolean, subtract with this rectangular cut, enter. Now this is the structure of this dual band PCR. Okay, this one, which is having ground plane, then substrate, and then the resonating structure, which is aligned with this U and V axis, not in X and Y axis. Now we have to put its frequency and boundary conditions. Then go to the simulation. Okay, go to the simulation. In the simulation, here in the simulation, the frequency term is okay. We have to only simulate this unit cell only. So by using the Fluctuate put, we can simulate it easily. So this x-axis is unit cell, this y is unit, and this z-min is add open space as add open space. This is same as absorber. Okay. Plus z-max. Z-max direction is my Fluctuate port direction, where we have to place our terahertz source. Number of Fluctuate mode is 2. One is for TE and one is for TM. Now press OK. Fluctuate port is assigned. See this in the port. This is my port 1. Z axis from plus Z to minus Z. And this is Z min from minus Z to plus Z. Okay. Port is also completed. Now we just have to simulate this structure. Just simulate this. I have the simulation file. The simulation is started, but I have the simulation, this PCR file only. Okay, the same structure is here. Yeah, all the final results are there. So first check the 1-day result. First we have to check all the S parameters. Then by using this post-processing term, we have to put our equations, what we have to calculate. So just go to this 1-day result. In 1D, this S parameter, there are all the 16 S parameter combinations are there, which are covering its Z-max and Z-min direction along with this O and cross terms. Okay. So this I will directly show you the equations. All the terms are there. This Z-max 1, Z-max 1. What does it mean? this is the co-reflection, because I know I am placing my terahertz source along in the ZMAX direction, and in the receiving side I receive my signal in the ZMAX direction only. That's why this term is this is a reflection, and my incident signal is in one mode, and in the reflection the incident signal is also showing the one. That means this is the co-type of reflection, and similarly all the terms are there. All the terms are mentioned, all the 16 possible F parameters are there. So this result is also simulated. Here only 8 parameter will come. I will told you that things earlier, like why here only 8 part is there and in this PCR all 16 part is there. Because uh, right now I am simulating this structure by placing the terahertz signal in the ZMAX direction only. Because I know in the ground plane there is a metallic ground patch, so no need to take the reverse side of incidenting the terahertz signal. There is no use in this structure. If there are some resonating structure on the back side also, if there are some resonating structure, then we have to make a fluctuate port in both the uh, z-axis side, and we have to check all the 16 possible combination which are shown here. Okay, so after that, after this S parameter, we have to check its PCR curve. What polarization conversion ratio, how much ratio we have achieved with the help of this type of structure. So for that, see this structure. In the dual band PCR, go to this post processing. Okay, in the post processing, result template. In the result template, go to general 1D. In general 1D, go to mixed template result. And here you have to put all your S parameter and make a formula for calculating the PCR. So go to the paper and see the formula, what we have to choose. This is the formula. This is reflective type PCR. Then this R term is there. Only R term is there. Only we have to take care about the reflection coefficient. And if this PCR is as a transmittive type PCR, then we have to take the transmission coefficient as well, means S21 we have to take care. So right now this structure is reflecting type. So I have to take care only S11 parameters, means reflection coefficient. And for that we have to choose our polarization as well. So what does it mean? This XY means how much components are cross polarized in the reflection term, divided by what is the total reflection parameter. This is the total reflection, and this is the cross reflection only. Okay, so choose accordingly in this. So in this A, what we have to choose for all these 8? A, we have to choose this term. Reflection is 2, 1. S11 cross. And this is S11 co. And in the formula, there is a mod present. And because of this mod, we have to take care of the ABS term, absolute, and the square of this absolute. ABS of A square divided by, in bracket, there is ABS A square plus ABS of B square. I think it is clear to everyone why I am applying this formula. ABS A square divided by ABS A square plus ABS B square. This is the total reflection coefficient, and this is the cross reflection coefficient. And take its mod, and the square of this will give you the magnitude value of the PCR term. Press is OK, and then evaluate. This is the result. This one. From 2 terahertz to 8 terahertz, there are two resonating frequency will take place. One is here, and the second one is here. And in all these two frequency, our PCR value is more than 90%. More than 90% conversion we achieved. Okay, this is the formula for PCR. Just close this. After pressing this M key, you can check its value also. Snap to extreme. Snap to extreme. So till now we have covered the basic concept of PCR, then the simple design of a dual band polarization converter, then its boundary condition and the formula, how we can calculate its polarization conversion ratio term. Okay. Here theta term is there, phi term is there, but we know our structure is in such a way. This is my PCR structure. Our structure in such a way that it will make our copolarized component into cross or cross into co. So, and when we are calculating the polarization angle stability, then we have to take care our result with respect to this angle, this angle, this angle. This is the PCR 45 and this 90. So we don't calculate in the PCR design. Okay. But we can check its stability with the help of incident angle stability. For that, we can change this theta term. I am already explained the how we can change the theta in simulation as well as in experimental point of view. Okay, so I'm not covering this part here also. Okay, this is the basic term. Now, if you want to check right now, this PCR, this is the PCR design along this X and Y axis, because its length and its width are aligned with the help of this X and Y axis only. And if you want to check its all the U and V component, then you have to rotate this structure in the X and Y axis, and then you can calculate those terms as well. Okay, all these terms you can also calculate. This equation, with the help of this PCR and CST, we will also achieve. This is the VV and UV term. You can make this structure in along the X and Y axis. Instead of this X and Y axis, you have to put it along the U and V axis, and then you can calculate it. Okay. So this is all about the PCR. The only thing is this formula, how you can calculate the polarization conversion ratio. Okay, this is the unit cell. This is the multi-band polarization converter, reflective type multi-band polarization converter. And this is the another paper. This is the another paper, ultra thin reflecting. This is also a reflecting type of paper, ultra thin reflecting wideband terahertz polarization converter. And this is the wideband kind of terahertz cross polarization converter. Okay, I will just show you the basic structure. This is the basic structure. See, the previous structure which we will design here, this one, and this structure. Both are aligned along the U and V axis only. Okay, see this. So, with the help of this simple structure, we are getting the more than 80% of wideband polarization converter. Okay. In terms of this PCR, in terms of absorber, more than 90% absorption is required. But here in PCR, more than 80% wideband PCR is also acceptable. Okay. And all the rest, all the other process are similar. Just you have to make this type of a structure, then you have to simulate it along the x-axis and along the u-axis and v-axis, and all its electric component along u and v, and then you can find out its PCR value. Okay. This figure 5 is effect of oblique incident on PCR. How the incident angle will vary its PCR curve. Okay. Now the PCR term is over. If we have some time, then we will also, if we at the end of this session, if we have some time, then we will also make this structure also, this structure for achieving the wide band type of reflective polarization converter. But right now, I'm just coming into the bending process, how we can make a structure, how we can create a bending in any structure, any unit cell structure, along with any array structure for checking the structure conformability. Okay. Uh, we can also check in this structure. Okay. This part we will also cover. If there is a field monitor, we can check its. Just go to in 2D, 3D result. Here E field, H field and surface currents are there. Just directly click this term. And what's the PCR value? 2.9 and 5.9. 2.9 and 5.9. Yeah, this one. 2.912 and 5.9 something 5.905. Okay, these two are the main electric field distribution, main electric field, and we can check how this term will affect the resonating structure, these two frequency. Okay, let's see if again I'm again covering this term as well, because it is little bit difficulties to analyze the effective electric field distribution at the top of this PCR. Okay, when I am clicking directly this term, this window will open, and you can't observe the electric field distribution. So you have to check its absolute term, make the maximum as. See, all the fields are confined here along this axis. Okay, there we have make a cut along this U, or you can say V axis, not in the X and Y. See, see, in the first frequency, the complete electric field is confined along the V axis only, this one. And for the second resonating frequency, that 5.905, the electric field are confined along the X, along the V, and along the U axis. The diagonal part is important in PCR. Okay, this is the important things. So this is the electric field distribution. This is the magnetic field. In the electric field, in electric field distribution, at 2.912, electric field is confined along this axis, this. And in H field, for the same frequency, the electric field is confined along this axis. And for that, it is change. Okay. This is the complete analysis of the dual band PCR. We will see its 1D results in PCR formula and how we can put the PCR formula and find its polarization conversion ratio. And then we will also see its 2D results, where we have to see its E field and H fields for those resonating frequency that will resonating with the help of this unit cell structure. Okay. Now I am close this file. This one. Just close this result. Just a minute. Just a minute. Yeah. Now we will see how we can bend this structure, this unit cell bending. Right now it is a, see this one. Okay, this is the plane surface. No bending will take place till now. For this unit cell bending, you just select the component which you want to bend. If you want to bend only some part, then you have to choose only that part also from your component library. From this navigation tree, you have to select those structure only. But I want to bend my structure with this ground, substrate and resonating structure all. So for that, we have to choose this component. If I choose this component 1, then all these 3 parts are covered with this component 1. Okay. First, choose this component part, this one. Just go to the modeling. In the modeling, because this bending is a part of modeling. So for the bending, we have to go to this modeling part. In the modeling, there is a bending tool, this one. Okay. Cylindrical bend. I just want to bend this structure in a cylindrical way. So the local coordinator system, this will what it is showing. The local coordinate system needs to be enabled to use this functionally. Would you like to enable it? Yes, we have to create a new coordinate system for this bending. So this is the new coordinate. Generally, we have this type of coordinate system where the X, Y, and Z axis are there. But for this bending purpose, in the center, in the center of this structure, there is X, there is U, V, and W terms are there. Okay. Now, when I'm clicking this cylindrical bending, this type of window will come. This type of. And here, see this one, the lower side of the bottom of this structure. This is my unit cell structure. See its bottom. Only half part is covered with this orange area. Okay. Only half part is covered. And why this is happening? Because the impact direction, this is the impact direction, first section. This is the impact direction. Impact direction, only one-sided I am choose here. By default, it is only one directional. And if only one direction is choose, then any angle what you want to, how much angle you want to select for this bending, only the half part of this positive axis, this uh, right hand side, only that part is moving. Okay, so we have to choose. I will show both the term. I will show the both the terminology how it will behave. So I just have to choose the two-sided. Just take this. See, after choosing this two-sided, all these complete component, this complete area, all these part is uh, covering with the orange part. Okay. See, so that means right now when I am changing any angle for this bending, when I am choosing any angle for this bending, so both that part will take place for the bending, both the side. It will bend. Okay. Now this one is clear. This thing is clear. One-sided and two-sided. What does it mean? Okay. After that, there is a bending parameter. There is a two type of bending parameter, and in general we are choosing this angle only because it is very simple to analyze how much angle you want to bend. If your if you want to place your surface in a in such a type of structure where the more bending is there, then you have to bend it more. So accordingly you can choose your angle. Okay. And if you see your structure from the top, means if you see the top view of your structure, and two type of bending will take place. One is in the upper side, means in the positive uh, z direction. This is the positive z direction. This one positive z means in the this w direction. This is my positive w direction, and in the below side this is my negative side direction. So two types of bending is possible. One is positive w side of bending is there, and another is negative bending, negative side of this w, or in general we can say negative z axis bending is there. Okay, so that means for these bending parameters I have to choose this angle term. Just choose this. See, this is the angle, and right now it is placed with this type. Okay. Now choose, put any value. You can put a variable also, because in every point of time after design, at the time of designing, at the time of theta and phi variation, and in the previous lecture we will also see at the time of chemical potential and relaxation time uh, mm, point of view. In every cases we are choosing the variable value so that we can change it accordingly at any instant of time. Okay. So first I am telling you with direct value, direct angle value. Then after that, we will see how can we make a variable and how can we shift it with the help of parametric sweep. So in the angle, if we put the 45 angle, just see if I am putting it 45 and I will preview, I just want to preview my structure after putting the angle of 45 degree of bending and my impact direction is two-sided, then what is the condition of my structure that I will see with the help of this preview button. This one. See, just try to analyze it. Initially, it is putting on that surface, this one, this red one. Initially, it is here. And after applying the 45 angle, it will move like this. If I am applying the 60, okay. See, my angle is 90. My angle is 90. Then from this, with the help of this two-sided, in this axis, in this side, 45 degree of angle is created, and in the another side 45 angle is created, then it will make a 90 degree of bending. Likewise, we can change our bending. We can also choose a negative bending also. This is the positive bending where the structure is bent along the plus z direction. Okay, this type of structure. And we can also choose negative angle -40. See this one. This is the structure. -40 showing like this and +40 is like this. Okay. So you can make any type of angle here. Like -50. Just take preview and see this. And after observing these type of both the type of bending, after observing both the type of bending, we can observe in most of our practical cases, in most of the practical cases, we have to bend our structure in this way only. Suppose you have a surface, you have a meta surface, and you have a wall, or you have a pillar. This is a circular shaped pillar, or this is the surface of any craft. Okay, this is the circular shaped structure for any craft. So you have to place your structure in this way only. Okay. So bending, we can conclude our bending. There is two type of bending which will take place. One is on, if you see your structure on the top of the surface, then the two type of bending is, one is concave type of bending and second one is convex type of bending. Okay. So the main point is put your angular value with negative symbol so that you can place your structure here. This is the only single unit cell. If we make a multiple array, then we will see the complete area. This is this orange circular path. This all things are completed from this side also, from this side also. Okay. So right now I am placing the value. I just put its name as bend angle. Okay, just review. Bend angle value is 10. This bend angle value is at that time, bend angle value is 10 degree. 10 degree means 5 degree from left hand side, 5 degree from right hand side. So the complete bending is 10 degree. This we can also observe using the parametric sweep. Go to the home section. In the home, go to this parametric sweep. Okay. In the parametric sweep, new sequence, new parameter, bend angle. Okay. Bend angle is 60 from minus 60 to 60. From minus 60 to 60 with a step size of 10 degree or 5 degree, whatever you want to choose. Okay. In this case, after this 13 linear results, right now, Abhishek, I am in the lab, so I don't have the host access so that I can unmute you. But after the completion of my this all these session, I am unmuting you, and then you can ask your query. Or if you have any doubt, you can uh, write your query in the chat box. Because for this CST and HFSS, I am in the lab, so I can't access the host system. You can ask your query in the chat box. I just wait here. You can ask. When we have to simulate the bending analysis of 3x3 array, the structure become like a cloud shape. When we have to simulate, the structure become like a cloud shape. Okay, just a minute. After this unit cell, I just make a array of 3x3 of this structure, and then I will bend this structure in a bending way. Then you may ask your query. Okay. And the better way is for the simulation, don't simulate your structure in 3x3 array. Just make a 1x3 structure and then simulate it. I will show you just a minute. When I am designing an array structure, then you can again clarify your doubt. Just a minute. Yeah, just wait. So here the bend angle should be minus 60 to 60 with 10 degree of angle. Okay. Just start. Sorry. About entire sweep. Bend angle should be 0 here. Okay. F7. I just have to check only, not to start. Okay. I just make a copy of this structure for the unit cell and then we will check its bending analysis. Okay. Just close this. This bend angle is 0 here. Okay. For this unit cell, first I am make a array of 1x3 where the three component is placed one by one in a single row, like here also and here also. Okay. Then we will come to the 3x3. Because the better way is design a 1x3 or 1.5 type of array structure for the bending analysis. Just a minute. So component 1, transfer, translate, make a copy, paste it here 20 in the U axis, because right now for this structure UVW axis is there. So just make it and press OK. Bending angle is the angle between which two straight line. Bending angle is the angle. This is the, I will say just a minute. Okay, just a minute. Just a minute. In any standard paper, when you are where the bending analysis is there, where you see the some schematic diagram in which they are clearly mentioned what are the bending angles. So suppose Okay, this is my x-axis. Similarly, this is my x-axis and the other one is my y-axis. Y x. Initially, my structure is placed here. This is my structure. Okay, and if I want to make a bend on this structure, then what we have to do? We just this is the way, or this is the way. This is the answer for your question, Abhishek. Bending angle is the angle between which two straight line. This is not about any straight line. If we bend the structure, then yeah, angle between this and this is, if we make a axis for this surface, this bending and the bending design axis surface is this. Suppose this is my x dash, or if we make a direct straight line here, then the angle between this x and x my dash, this will show you the bending angle. And here also, in some paper, these type of structures are there. Okay. You can also observe, if you have some array type of structure and if you want to make it as a bending, then why you are bending? Because you have to uh, place your structure in any surface. This is the surface. This is the surface, and on the top of this surface, you have to place your structure. And when you are placing your structure on that curved shape structure, then the angle between this initial x-axis, the initial horizontal axis, and the axis which are creating right now, the angular difference between these two is the bending angle. Okay. Again, just yeah. Okay, this is clear. Now we will come back to our this structure, and we just try to make a 1x3 array structure. So just go to transform, again translate, right in this time t, then preview, directly press OK. Sorry, I'm not creating a copy of this structure. So just yeah. Just make a copy and then translate your structure in the x-axis. Then press OK. Okay, these 3x3 array structure are there. First, make a just add these grounds. Take this plus. Okay, now add these three resonating structure. Here add these three substrate. Okay, now this is my 3x3 array structure. Yeah, okay, Abhishek. Now click this component, then go to the bending, click this cylindrical bending, two-sided, angular, and make a minus 90 degree of bending. Preview. Just see this. So this is the bending angle, this one. Initially your structure is placed in the initial x-axis, and after that, after the 90 degree of negative bending, that means the positive this uh, bending angle in actual bending angle is 45 degree only. 45 both sides. Just because you already simulation is same. For this simulation, you just have to, if you have a single unit cell, then you can simulate it using fluctuate pot only. And if you have the array of your structure, then you can simulate using this uh, waveguide port. And that's why I am telling you ki don't put this angle directly. Put a variable here, then go to the home, then go to this parametric sweep, and in this parametric sweep put your variable value and then simulate. Likewise, I just show you how much variations are there. 13th linear sweep I have to I just gave it in the previous simulation result. You can directly simulate this structure. Next question is how to bend the structure along y-axis. Along y-axis, if you want to make, because here the structure is cylindrical, which is same. Okay. And if you want to make your structure along the y-axis, then first you have to change this phi angle and then you can simulate. Okay. Because in every time our simulation will take place along these direction only, along this direction only. First, using the polarization angle, you have to change your structure, and then you have to apply the same concept, same cylindrical bending. So your structure will simulate along your y-axis instead of x. So you have to change this phi term. First you have to change this phi term and then you have to bend your structure. Okay. Bend underscore L. See, bend underscore angle. Okay. Go to this home part. Parametric sweep. This is the 13 bending angle which are already applied here. First check this. No, have some mistake. Just a minute. Yes, yes, yes. I got your point. I got your point, Abhishek. For the array structure, the problem will arise because it is bending for a single unit cell only. And for every case, it is showing the different uh, bending combinations. But if directly, if directly by using the single unit cell, with the help of single unit cell, if you are making a array of this type of 1 cross 3 or 3 cross 3 structure, and then you are simulating your structure for the bending analysis, and if the multiple different bending will take place, then there I have to check this for this type of direct doing this type of bending. But we can also we have another option. We can directly create a one substrate here. Means analyze your structure by making a 1 cross 3 unit cell uh, at the time of designing, not first design the single unit cell and make a copy or rotate or mirror. Just assume that this is your unit cell. This is your unit cell which have a rectangular type of substrate and ground, and in between this there are three hexagonal rings. At that type of for that type of analysis, you have to make your unit cell like this only. If I am assuming this is my unit cell, then you can bend it, this structure also. Hmm. And one more thing is there. I just show you what mistake we can see. Why this is happening? For every unit cell, no, this is not the perfect way. Why it is happening? I will show you. Just go to the history. Delete this. Rotation cylinder. Define cylinder. Rotate. Subtract. Subtract. Define brick. Rotate. Boolean subtract. Define frequency. Transform. Ground. Substrate. Ground 2. Okay. Okay. Now go to the home. Parametric sweep. See, I think this is the solution for your query. Okay. And why this cloud shape structure is there in the initial file? Because in the same file for the unit cell, you are applying one bending analysis. Okay. And for the same unit cell, you are creating a array of the structure, and again you are applying a bending. So two type of bending will apply for this structure. So the final array bending will also happen, and simultaneously the single unit cell bending will also take place. That's why there is a cloud shape structure that was shown earlier. Okay. So if you want to make a bending analysis for single unit cell, then make a single unit cell and then apply the bending analysis. And the second thing is, if you want to make a want to check the bending analysis for a array type of structure, then directly make a array of the structure and then apply the bending once only. If two type of bending, two times you have applied the bending, then two bending will take two bendings performance will apply in this structure. And that's why after this issue, I am in the history list. I just delete our first bending process. So only the array type of bending will present here. Okay. I think this is the solution for your query, Abhishek. We will also check this bending for 3 cross 3 also. We can check. But for this, again, delete this bending performance first, so that only array structure, till array structure we are at this stage. We have only the 1 cross 3 array, and now we have to make a array in the y-axis. So just go to the translate, make a copy in the y-axis. Okay. Again, make a copy for these three structures. Directly put your value. Y20 in the positive y-axis and press OK. Make a copy, and then put the tentative value, review, and OK. That's it. Add all this. Add these three substrate. This is the 3 cross 3 array structure. If you make only one side, then see after this preview, this structure is in its plane only, and after this positive side, the positive x side, the structure will rotate here. Okay. So better way is bend angle. This is the surface. Okay. And if this type of structure, if you want to simulate, then suppose this is a structure and you are making this structure as an array. So without using the Flockpad port, without using the waveguide port, you can't simulate this type of structure. Okay. So in the simulation, go to the boundary condition frequency value is saved, this background, electric in the x-axis, our ET component will 0, in the y-axis our HT component will 0, okay, like this, and in the Z-max and Z-min direction I am placing a open add space condition here, like this, okay. This is my ET0, this is my HT0, this is open add space, press OK. Now go to the waveguide port, put it in Z direction, Z negative, the X min and XY 30 is okay. This Z position is okay. Directly apply in the negative again, okay. See, this is my 3x3 array structure. This is the waveguide port which I am applying for this 3x3 array structure. I am already applying the bending angle here for the calculation of bending. Just directly go to home, parametric sweep, and you can simulate your structure. Okay. This is the process how to bend the structure. It will take lots of time. That's why I'm not simulating this structure right now. Okay. This is all about the bending concept. For today, we have covered the PCR and the bending. Okay. Now, I just switch my screen to one system to another system, and I will show you the basics of HFSS and some steps should be followed for transferring your design from CST to HFSS and from HFSS to CST. Okay. How much time it will take to simulate 3x3 array structure? There is no fixed answer for this question because it is depending upon many parameters. First thing is your system capability and all the other thing. And the second thing is your structure complexity. Because for any simulation, the system, the CST will make a meshing of all these structure. And after that, it will simulate your structure. And some more parameters are there, whether it is using tetrahedral hadron meshing or any other, or there are some other things should be there, whether you are using the adaptive meshing or you are directly without adapting meshing, you are simulating your structure. That all are depends for the simulating time point of view. Okay, so it depends. Mainly it depends on your structure, which type of structure you are using, by how much complex the structure is, and how many layers you are using. If there are multiple layer, then it will take, if there are multiple substrate layer or there are more than 2 to 3 resonating structure layer, means in many paper you have seen this thing. They are using multiple substrate layer, and in all the substrate layer there are some type of resonating structure present, which are responsible for different application, different frequency band. So every thing is counted for the simulation time of any structure. Okay, so we can't uh, uh, make our statement to how much time it will take. Okay, I just take 5 minute break here. Then I will start the HFSS and how we can directly, because we are creating our structure in the CST and we want to directly place our structure from CST to HFSS or HFSS to CST. That is important. That will helpful for the any type of design in CST and HFSS also. The only thing we should take care is the uh, condition, boundary condition, and all the other simulation type of setting, which we have to apply separately. Rest, all the structure, we can directly transfer. So I just take 5 minute break here. Then I am start my session. Yes. So now just take how to first I am taking this thing how to design from CST to HFSS. Transfer your design from CST to HFSS. Okay, because in this screen I am open my CST software. So first I will show you what file we have to export from this CST so that it will contain our design part. This is very complex structure where we have assign our port. So I just open the our previous structure, the absorber structure. That okay. This is the structure. First, go to this navigation tree, this component. Okay, open this component. Take this component part complete with the ground, substrate, and all the circle of this metallic ring. Okay, this component part you have to select. Then go to this modeling, because this modeling is responsible for all the designing purpose. Okay, import export. Go to this import export section, because from CST we are exporting our design. So go to this export part, this export. Okay, this 3D files. In this 3D file, this SAT and SAP file that we have to choose. Okay, I just save it in desktop. My file name is Tuesday CST. Okay, type it SAP, and here you have to choose your HFSS version. Okay, I think we have HFSS 15 version, so we have to choose this. This is your HFSS version where you want to open your file. Okay, then this save button. Now this is the file. This is your SAP file. Okay, I just copy it. I just copy my SAP file from here. Just copy. Just paste it in my pen drive. Now in the another screen where I am opening my HFSS software. Okay, So I just stop this screen and I am opening my another screen. Just a minute. Yeah, it is visible now. Okay. So here, this is the uh, another system where I have to open my, first I have to open the HFSS. Okay. And this is the HFSS software, ANSYS Electronics, ANSYS Electronics desktop. This is my uh, HFSS software. The only thing from CST is we have to fetch the SAT file, SAP file. Yeah, this one. Just close this. After opening this ANSYS software, this screen will come. Okay. In this, uh, just go to this project. Okay. In project, you have to open the insert HFSS design. Just open this. It will take some time, just a minute. Yeah. This is the screen for HFSS. Okay. Here multiple options are there. Similar, the same for the CST. All the tools, HFSS, draw, project, file, edit. Here some shapes are there. Okay. And the pan, rotate, that view portion is there. Okay. So what we'll have to do, go to this modeler, this one. In this modeler, now initially in this CST, we are exporting our design. Okay. Here in this HFSS, we have to import it. Okay. The system will come. Go to the software. My pen drive is not showing. Just a minute. Yes. Go to this modeler. First, you can choose your unit in the modeler. Here, this is units. So select unit. Our unit is in micrometer. Okay. Unit is in micrometer because in CST I'm working is in this design is in terahertz. So all the dimension should be in micrometer. So choose this. Then okay. Then go to the modeler. Then import the file in my pen drive. This is my SAP file. Okay. Now this is the structure. This is the complete structure. But as it is importing from another system, another software, so all the materials are same. Okay, the resonating structure and the substrate and the ground all have the same material. So the dimensions are similar, which are in CST as well, but we have to mention its material value. Okay, so see, this is the template, this is the view. Just like in CST, we have navigation tree. Here we have this options, all these options. Okay, so this is our ground. This is substrate, and this is the outermost resonating layer. This is the mid one, and this is the last one. These 6 things, these 5 things we are importing. So suppose this is my ground. See, this is the ground. So click this. Okay, and here is the option material. Just go to this option in the material section, edit, and what material you are choosing, search by name, gold. So click hold. Okay, so gold is placed here for the ground plane, and the color you can also change, and the transparency you can also change. All these 3 things you can change here, but you can't change its dimension because it is already importing file. Okay, so just click this OK button. The ground is assigned with gold material. Okay, now this, yeah, here, this is the ground which is having the gold material. Okay, second, this is the substrate area. So we have to choose our substrate. Go to the material section, edit, and if you are already using some material, then it will come here. Vacuum is by default, and we are already using the gold material. So in the edit section, this polyamide having a relative permittivity of 3.5. Okay, this is the polyamide. Polyamide is applying, having color this. We can make it transparency also. Okay, so we have transparent some part of this substrate. That's why our ground and metallic and substrate, all the part are clearly we can observe. Okay, this is gold in which our substrate ground is there. In the polyamide, our substrate is there, and rest all these 3 things we have to apply as a metal. Gold directly here also gold. Just press OK, and this is gold. Okay. This is the complete structure. Means if you are importing some structure from CST, then in CST you have to make a you have to save the file dot sap file, and in HFSS in the modeler we have to import that file only, and uh, after importing this file, all these have a same material. Okay, so based on your initial version file or your structure, you have to mention the substrate material. You have to mention all these materials value. Okay, design part is completed. This thing is done. Okay. And how we can assign this is the, and in CST, in HFSS, in CST you can apply the boundary condition very easily, because in CST multiple options are there in the boundary conditions, and directly you can tick all these fluctuate port or ET0, HT0 and unit cell, open add space or directly open all. You have all these options. You just have to select those options and you can create your boundary conditions accordingly. But in HFSS, you have to make a boundary condition here. You have to make a boundary here. Okay. You have to make a boundary whether you want to, because in the x-axis, see, this is here, the axis is also present. This is my x-axis, this is my y-axis, this is this direction, my x-axis. Here this is my y, and in the topward most direction, this is our z direction. So in the x and y, we have to choose the same thickness and width and height. It must be there, the L and W. And in the z max direction, we have to make a boundary like the box shape structure, in which we have to create a free space or vacuum. Okay, so that one can easily make a boundary box here. Okay, in between you have to make a vacuum or free space, and then you have to place the lattice pair of the ET0 and HT0 in the x and y axis, and in the z axis you have to make it the we have to put your fluctuate port in the z max direction. Okay, that is that are little bit challenging part for assigning the boundary condition and the fluctuate port, that we will cover in the uh, next tomorrow session, so that we can directly make a boundary box and we can directly simulate those structure, and we can check its all the parametric results, what whether the similar result will come or not, and how much the port distance we have to assign. Because in CST, when with the help of your unit cell structure, with the help of your unit cell structure and with the help of your frequency sweep, means your operating frequency band, it can calculate its mm, port direction, port distance, how much port distance we have to apply. But in HFSS, you have to take care those things by its own. Okay, means whether you have to put your fluctuate port in 5 mm or 7 mm or 90 mm, that you have to calculate with the help of uh, your frequency and your resonating structure. Okay, now this is my structure. Okay, this is my HFSS structure, and here we have to just select this modeler option. Okay, just select this modeler option, export. Yeah. Mm, in the previous step, I am exporting my file from CST and I am importing it in HFSS. Now in here, I have to export my file from HFSS and then I have to import it in CST. Okay, means I am just doing a uh, reverse process. Okay, so for this is my modeler. Okay, again go to this modeler, this export. Now I have to export it. And what we have to choose here, go to the, yeah, I am saving it in my pen drive only. Okay, file name, Tuesday underscore HFSS. Okay, and here save as type. Just a minute. Okay, sorry. So this is my file where I am exporting our HFSS structure, and my file name is tuesday.hfss. Okay, and mm, from CST, I just choose this SAP file for extracting the design. For here, I have to choose this. Here also it is, just a minute. Okay. In some previous HFSS software, there is a .sm3 file, but here it is not showing any sm3 file. So we can check by using this .sap file. Okay, just save it. We will see its a boundary condition and its simulation in the tomorrow's session. Okay. Now I just close my this window. and open this. Okay. Just close all these CST files which I have opened earlier. Open the fresh file. Frequency domain. This is because we don't know what frequency it is right now. I'm just checking with the help of this SAP file because .sm3 file, it should be there, but I'm not sure why it is not showing here. So we will check. Just directly go to the modeling, then the import export. Okay. .3D files here. This I'm just checking. I'm not sure. What is the file name? No, it is not showing because it is only showing the .sec3 file. Import fail. Okay. I will just check how we can extract the HFSS file from HFSS to CST. Okay, because I know there is a SM3 file, but in my system, this SM3 file will not show. That's why I have some doubt. So I will look in this. Don't worry. So rest all these HFSS concept and the exporting some file from HFSS to CST that we will see in the next lecture. Okay. In this lecture, I am covering the PCR, all the terms of this PCR for the wideband and for multiband how we can calculate its PCR value and its formula, how we can apply, and what should we take care for extracting the co and cross component of these S parameters. Then we will also see the bending, and there are some error. If one bending is present, then we have some problem of second time of when we are doing the bending process. So that we have to take care. If your one time bending will completed, then you have to remove that part from the history list. Then you have to simulate another bending. Okay. And we will also see the array of bending in means all type of bending we are covered. We are covering the unit cell structure bending. Then we will cover the array 1 cross 3 array structure. And then we will also cover the 3 cross 3 structure. Then we will see the basics of HFSS, how it look like and what are the all these parameters, all these terms and tools are there so that we can use it in the designing process. And uh, one more things we are completed, uh, transferring of the design of CST file from this CST to HFSS by using the SAP file. Okay, that's all from my side in today. And in the next lecture, in the next tomorrow lecture, we will directly cover the first we will see the how to export the HFSS file in the CST. One thing that we will cover, and then we will directly make a absorber structure from the start from the basics in the HFSS, and we can also see how we can apply the fluctuate port boundary conditions and all these fluctuate port and the master slave. Here master slave boundary condition we have to apply. That we will see and simulate in the next lecture. Okay. So if in today's lecture, if you have any doubt, you can ask or raise your hand. If you have any doubt, you can ask in the chat box. If you have any doubt regarding the PCR or this bending or the basic HFSS transferring technique, then you can ask. Okay, I just wait here for 5 minutes. If you have any query, you can ask in the chat box. Otherwise, we will conclude this session here and we will start our next session in tomorrow 9 a.m., which is the technical talk. Okay, I think there is no more query for today's session. So we will conclude our session here. Thank you, everyone.